complex ions, right? And this is a complex ion with cobalt, that's pink, complex, that's blue. When it's at equilibrium, it's in between. Is that purple? I don't know. Okay, cool. Now, we're going to test and drive the reactions. Let's go through this. Let's go through this. So here's my first test. Okay? The first test is I put in, let's take away the sound. The first test is I'm going to, I don't know what I'm doing. Oh, I'm adding hydrochloric acid. So what happened when I did that? What's the color change? Start again. Here's tube 1. I'm adding hydrochloric acid. What am I really delivering? I'm increasing the what? Right. If I'm increasing the reactants, what's happening to Q? And therefore the forward reaction occurs, which means I make what? Blue. Or, hey, if I increase Cl, the reaction shifts to what? Make less of it by shifting that way, right? Pretty simple. Okay, next test. There's my hand. Test 2. I'm adding calcium chloride. Mr. Grodsky, calcium's not in here, correct? So therefore calcium's not in the Q. But what is calcium chloride delivering? Ah, so it's called a common ion effect. Calcium, by adding calcium chloride, calcium has no effect. You need to know that. But the chloride ion it's delivering, look closely. Come on, bring it up, Grodsky. Whoa! Okay? Look closely by the beads, as my phone will not. Come on. Come on. Come on. Yeah. Okay, so by the beads, what color is it? Blue. Why? By adding more chlorides, whether it's HCl delivering the chlorides or the what? Calcium chloride, I'm making the what? Q smaller, correct? Good job. All right, moving forward. Yeah, it's enough, Grodsky. Okay, now, I'm going to start with blue. In this test, I'm going to add, this is important, this is last night's stuff. I'm going to add some water to this. This is not the one I wanted to do yet. Okay, if I add water, I'm increasing the products, right? Yeah. So what am I doing? Making the Q greater than K. And so what's going to happen is the reverse reaction. So by adding water, what's happening? I'm shifting it this way because now Q is what? Greater than K. Cool beans. Now the fun one. Okay? The fun one. Let's do it. Come on, move it away. Let's get to it. Stop talking on here.
Is there nitrogen, oxygen, or fluorine?
No. Okay. Come on. Next test. I guess we're absorbing that all in. That was too great to understand. So here we go. We're going to make this guy blue. So we're going to add some hydrochloric. We're going to add hydrochloric acid first. We're delivering HCl. Boom. And now hydrogen's not part of this, but the Cl is. So we're making it blue. We're driving the reaction. Q is now greater than K. Swinging this way. Now we're going to go back the other way. And what's cool is I'm going to add silver nitrate here. AgNO3. What does this break apart into? Ag plus. And Ag plus is insoluble with the what? So by adding Ag plus, I'm making a precipitate. And the precipitate's going to take out the chloride. Watch the solid appear. See the solid start to appear? Remember the yellow stuff that became a solid? A precipitate is occurring. What does that mean? The chloride ions are attracted to the silver plus, and they're making an insoluble compound. And if I take out the chloride ions, where is this reaction going to shift? Yes, because by lowering one of my reactants, okay, I'm making the entire expression bigger. If I take out the reactants, isn't this expression too big now? And the reverse happens. So as I keep adding more and more, bring it up. Whoa, okay? You see that it's getting pink. Okay, but that's not what I'm after now. This is the best one here. Okay, so I've got this test tube, and I've got hot water. Listen, this is a skill you have to have. Okay, I'm going to show you that it's warm, maybe. Come on, give it to me. So it's 76 degrees Celsius. Pretty hot. Okay? As this entire course is, right? All right, now, I'm going to put this sucker in hot water. The reason I'm doing this is I'm asking my students, is this an exothermic reaction? Is the heat here? Or is the heat here? Am I shifting this equilibrium? Am I shifting Q here? I'm changing the heat. What am I shifting? The K. Hey, what's happening? It's going what? Blue. We see that more products are being favored. Why? I added heat. Heat always favors the exothermic or endo. If you think the heat is here, by increasing the heat, wouldn't I have to lower the heat by going this way? Did it go pink? No. If the heat is here, endothermically, if I increase the heat, don't I have to lower the heat by going in the blue? So where's the heat in this reaction? On the reactant side or product side? Reactant side. So the forward reaction is endo or exothermic? By that endo. Let's do the opposite. Okay, this is a cold water bath. What did we learn? On lower temperatures, we favor the exo or the endo? Exo. Take the heat away, you're going to make more heat. So I have something blue. If the heat is on this side, party people, isn't the exothermic the reverse reaction? And shouldn't I move? Now, it's not shifting Q. I'm shifting what? The K position. This is going what? Pink, because the K is favoring at lower what? Temperatures, the reactants more. This K is actually moving. You change temperature, you change the value of the K position. Which way? Depends if it's exo or endo in the forward direction. You get that? So both of these tests did what? Show you that the heat belongs on what side? Left or right? No. Left. It shows you the forward what? Reaction is endothermic. That's a skill you must have. Why? Because under cold conditions, we favor the exothermic. If the heat's over here, remember we heated it? It went that way. You add too much heat if you do the Regent style, you lower the heat by using it up. Both of these tests prove the forward reaction is endothermic, and all the guys involved are taking their bows now. Okay.
How did they just get there?
Okay. Whoa. Okay. Now, party people, let's do this. We're almost done with this, and we're going to do some classwork. Oh, Christmas in July. Here we go. Last little piece. I know I'm pounding this home because, hey, I'm tall. Let's go to 62 here. All the way down. Okay. We're going to go to NO2 to N2O. All right, party people. I've got for you today an ampule. This is an ampule of NO2 and N2O4. Okay? Let's get rid of the stuff on here. Now, what's in this ampule? Two gases. Those gases must be what? In equilibrium, correct? So what do we got? We've got, party people, NO2 in equilibrium. It's not a what? A K value that's so extreme, so it's not a completion reaction, N2O4. And this is pretty cute because to do the Lewis dot diagram, N has 5 valence electrons, right? 1, 2, 3, 4, 5. This O, double bonds. Okay. This O, single bonds. And you have what? Well, what's weird is this has 7. Not very stable. N wants to have what? 8. But if another NO2 comes together, it can make a dimer and stick together. So NO2s have what we call a free radical. But another NO2 will make a what? Bond right there, and it'll work very nicely. So 2 of these stick together. Okay? And by the way, what's the hybridization here?
Wait, is that all unpaired?
That's 1 in there. So it's an orbital and is 1 unpaired. Isn't there 3 orbitals? SP, which means I have an unhybridized, allowing hybridization. Okay, notice the color. Notice the color. Okay, there's some delocalization that can allow electrons to move. Okay, any case, who's brown and who's clear? Okay, well, just so happens, okay, this is brown and this is clear. So are we in equilibrium? Of course we are. Okay, I'm telling you. Now you see, Mr. Grass, this is a colored glass. No, it's not colored. It is not colored. You see more brown than clear, but clear you don't. So it's hard to compete with clear, right? Any little brown will compete for the clear. By the way, this was the gas that came off of nitric acid. Remember nitric acid? We did like copper. This was the NO2 gas, but it's in equilibrium. And by the way, I have this wrong. I need 2 of these, right? Okay, Gratzky. Okay. Now, let's put this in an ice bath. Ooh, what are we solving for here? I want to see if the forward reaction's endo or exo. Yeah? Okay. I'm going to take this hot water that I have boiling here, turn this off, and hope we don't burn my hands. That's pretty hot. Ah! Okay. Hey, it's all good. Oh my gosh, the skin came off. Okay, no. Let's put, slowly, one of these into the hot water. I don't want to do it too fast because, yeah, it's probably tempered, I forget. All right? But I'm just putting this in hot water. Both of these tests will do what? Okay? Should be telling me the same position. I'm trying to find where the heat is. Okay? All right, now, let that sit in there. Hope it doesn't break. Now, this is equilibrium. This is ice bath. Who's lighter? Ice bath is lighter. So in the ice bath, hey, did this reaction shift with the temperature? No, it didn't shift. What moved? KQ. We didn't shift anything. We just moved the position of K. A shift does not occur with a temperature change. The KQ. Now it went lighter, didn't it?
Yeah.
So there's more what? Now there's more of these guys. If I've got more products, what just happened? K did what? Moved that way to favor more products. And all of a sudden, what? By K moving, is it now Q? We're now less than what? Even if we're right here. If I have Q right here, and all of a sudden I move the K this way, isn't the Q now greater than K? And that's what you just saw. It went clear. Hey, wait a minute. I took away the temperature. By taking away the temperature, what did I just do? By taking away the temperature, yes! Where do I put the heat? Where do I put the heat? Aren't I favoring the forward direction? Right! The heat belongs here. The forward reaction must be exothermic. Okay, well guess what? This should say the same thing. Ow, ow, ow. Okay, how about I just take the tube? Okay, here's room temperature. What did we get? We got dark. Why did it get dark? Why did it get dark? Because we made more what? Why did the reactants increase in number? Because the K did what in this case? It shifted. And when it shifted, we were at equilibrium. And then when I did what? Heated it, it shifted this way, and now what? Q was greater than K, and it worked to make more. We're not shifting because of Q, it's shifting because we're changing the value of K. And what does that mean? We favored the what? The exothermic pathway when we added heat. We favored the endothermic pathway when we took the heat away to make more of it. Okay? That is important. Moving forward. Now I want to review what we did last night. I spent all that time so you completely understand what Le Chatelier's principle is. Okay, so let's take on, all right, a new worksheet. Okay, here's what I want. We're going to do this one together. All right, equilibrium for number 1. Okay, so equilibrium for number 1. Oh, and by the way, real quick, another way to look at it. Because there was more, it wasn't all clear as brown, probably was more spontaneous in the forward, yes? And actually the equilibrium position is over here. K is greater than 1, okay? Okay, any case, let's go to this worksheet. Let's go. All right, let's get ready to do chemistry. Okay, now, you've been doing it. I've been boring you, I know. I feel bad. No, no.
Now you're over.
No, I'm definitely over it. Okay, so here we go. Equilibrium. Constants, 2. I think I'm going to view this one. Here we go. All right. Now, I'm going to do this right here. We're going to do it together. Now, this is our first type of equilibrium problem. Ooh, equilibrium problem. What does that mean? We're going to always work to equilibrium, and then we're going to have some values of K. We could change the temperature. All of this, you need to understand. Okay, now, let's go. Will a precipitate form? Okay, with the following reaction. What do we have? We've got lead nitrate, PbNO3, and there's 2 of them. And it's a Kardashian wedding with a rating. Is added to sodium sulfate. And that's going to be Na2SO4. Okay, the first thing I'm going to do is find my products. Now, I have to realize that this is a Kardashian wedding. They don't exist. This is really what? Pb plus 2. This is what? Nitrate ions. These are aqueous. I know I didn't put it there, but these are aqueous solutions, which means they're free ions. What else do I have here? Na plus, SO4 minus 2. And there's 2 Na pluses, and there's 2 nitrates. You get that. They're 2 clear solutions because the ions have dissolved. They're soluble. Now, when I poured them together, just by hook and crook by motion, the lead plus 2 is going to find a new what? Good. And the sodium could find this. And what we write in a lower level chem class is we just write what the switching partners are. We call this double replacement in Regents chemistry. We say, okay, we're going to make Na, who's plus 1. Hey, nitrates are -1, so we write a new formula. And by the way, it's aqueous. Group 1 ions have a small charge. Table L is given to you. Now, lead sulfate. Look at this. Lead is plus 2, sulfate's -2. Can you guess by Coulombic charges that will not dissolve? Correct. Lead sulfate is your precipitate. So I write solid. Now in truth, what is really this? You have free Na plus and free nitrates. So in real chemistry, let's do the net ion reaction, because that's important. What really is happening? What, isn't the sodium and nitrate always kind of flying, just kind of hanging out? It's not doing anything. So what really happened? Lead plus 2 plus what? SO4 minus 2 became what? Pb SO4 solid. These are aqueous ions. That's what happened. Now, what do they say? When the reaction reaches equilibrium, the concentration of sodium ions is something. Okay, now, when we deal with things that don't dissolve very well, we always write them a certain way. So I'm going to rewrite this. I'm always going to start with the precipitate first. So watch, I'm going to make this reverse. Now why do I make it reverse? Because we're going to do an equilibrium constant always with these types of reactions. This is an ionization reaction, or I should say a precipitation reaction. We always write them for equilibrium constants in the reverse. So I'm going to rewrite this. PbSO4 goes to what? Pb plus 2 plus SO4 minus 2. Why am I doing that? Because I want to write an equilibrium constant, double arrow, that reflects the ions always as products. In truth, we made a solid. Is it 100% solid, or did some of it really dissolve? Tiny bit dissolve. So really, I'm starting in this fashion, and it's going to break apart a little bit. Now, we say it's insoluble, but that's a lie. Okay? Now, what did they give me? Okay? Will it precipitate form? Okay, now, what did they give me? Well, we know we're reaching equilibrium. Okay? Now, what we're going to need here is, let's do an equilibrium of this. Remember, this is a solid, right? This is aqueous, and this is aqueous. What's the equilibrium? KQ is equal to what? Pb plus 2, concentration to the first power is equal to what?
SO4.
SO4 to negative to the first power. Because this is really a product of the ions that come out, we call this a KSP. It's still a K, but it's speaking to that reaction. Yes, Joe?
I thought precipitate reactions are completion reactions.
They are.
So how is
But we're going to use this little tiny K to answer something. It's not totally. We're going to try to solve for that little bit of piece that's going forward. So you're right. We can treat this completion. Okay, it's pretty extreme, but we're going to use it to our advantage. Just stay with me for a second. All right. So the KSP is equal to that. Only at what? At equilibrium. Are we at equilibrium? Yes. So here's what we're going to do. We're going to write an equilibrium table like you did last night. Okay, I'm going to rewrite this so I give myself some room. So PbSO4, guess what? It's a solid. I really don't care about that. But what do I have? Pb plus 2 plus SO4 minus 2. Now, I'm going to write an ice table. Ice, ice, baby. Okay, what'd they say? What do they want? Will it precipitate form? Okay? Now, they gave me the values of these. And they gave me the equilibrium concentration of the sodium ions. So at equilibrium, the sodium ions are what? 1.588 times 10 to the negative 3. That's equal to sodium ions. Is sodium in my reaction? In my Q and my K? But wait a minute. What did the sodium deliver? Right. For every 2 sodiums, there's 1 sulfate. So if I have this, what will be the concentration of my sulfate? Half that, correct? For every 2 of these, there's 1 sulfate. So what I'm going to do is take this and divide by 2. So 1.588, okay, second function EE to the negative 3, divide by 2, and I get the sulfate is 7.94 times 10 to the negative 4. Were you with me?
Yes.
Oh, wait a minute. Wouldn't this be initially 0? What's going to be the change? If I start with 100% of my reactant, KSPs are really small, right? So, but there's still a little tiny area of Q can be K. It goes forward a tiny bit. It's not A, it's insoluble. A little bit of ions come off. So it's going to go forward a tiny bit, correct? So this is going to be what? Plus X plus X. Wait a minute. Isn't this the value of the X plus 0? Isn't this my X? Why are they both X? What's the coefficient in front? Every one makes one of these. They have to be the same. So this is plus 7.94 times 10 to the negative 4. This is plus 7.94 times 10 to the negative 4. Plus 0, that's what? Both of these numbers are the same. Okay? You with me? Now, we're going to solve for my K. I know the concentrations of both. Let's go find KSP. So what am I doing with them? Squaring them, right? Isn't KSP the product over reactants? Coefficients become exponents. Solids and liquids do not apply. And who is a solid? He's not there. So the KSP or KQ is nothing. It's over 1. KSPs only have a what? A top numerator. The denominator is always the solid. That's why they always rearrange them. So let's go find it. KSP is take our 7.9 and square it. So my KSP is equal to what? 6.3 times 10 to the negative 7. You with me? I just got my K. Hey Joe, is that big? No, that's tiny. But is it 0? That means there must be some little amount of what? If Q has a little ability to go forward a little bit, correct? But not much. Okay, now, We have our K. We're almost done. Stay with me. I need my Q. Now, what did we add? That's the molarity. But wait a minute. We poured them together. Remember acid base? What's the new volume? What's the new volume? 0.5 liters, right? We need the new what? Concentration. So we take what? 8, second function EE to the negative 3, divide by what? That's easy, 0.5, right? Okay, so I get 0.016. Did I do that right? Okay, so I get 0.016. What's that equal? That's a concentration of what? PB plus 2, correct. What's my Q? Isn't the Q the same formula?
Yeah.
So it's that. Now what's the other one? I have sodium sulfate, right? So I have 5.0, second function EE to the negative what? Negative 3. Now I'm going to divide it by 0.5. Why? The new volume is going to be bigger. Molarity is that, right? Total volume. So it's going to divide by what? 0.5. And what do I get? 0.01. Why is this Q? Isn't this what we added? And isn't this what the nature allows? Let's go find the value of Q. 0.016. By the way, it's to the first power, isn't it? The same equation. Times what? 0.01. What do I get? 1.6 times 10 to the negative 4. That's my Q. What was the question, party people? Did this make a precipitate? Party people, look at the reaction. What if I say make a precipitate? I'm asking you, is this going this way? Or I'm asking you what? Was Q what? Greater than K. Look, Q is 1.6 times 10 to the negative 4.
Yes.
And that's much bigger. Q is greater than K. Q is greater than K. So the reaction's working in what? And therefore we are making a precipitate. Yes. Yes. Yes.